Thank you very much for being here. It was a great day. Some of you already told me that they are enjoying the conference. How is it going? Yes, okay, great. So we are here to talk about a topic that really turned me on. Is something unbelievable good because, as you know, I am enough old to remember the good old times of C++, C, and so on. So when I saw the new interoperability stuff, I was absolutely enthusiastic to see all the stuff that can give me more performance, to do also the nasty stuff. You know, I love to play with memory and to do everything I can do to improve my application and to have a better interoperability with all the languages. So let's see what happens here. First of all, I want to introduce myself. I am a Microsoft MVP. This means basically that I am not a Microsoft employee. Okay, I am a professional guy. I'm a consultant, a software architect. I work with many industries. The most exciting is the banking one. No, just joking. Of course, it's racing. That have totally different kind of domain of problems. And with a friend of that works in the racing, we created the Italian user group for C++. Yes, the language still exists. Yeah, absolutely. And we still enjoy writing code with this modern C++ stuff, which is unbelievable good. And can I say, I love playing with all the language. So one of the experiments that I did recently was to write a plugin for Node.js that can automatically give you the interoperability by generating code to call C# from JavaScript, including the asynchronous stuff and poking down with the libuv and so on. So it's kind of my kind of style, this one. And of course, I am a speaker because I'm here. And I travel all over the world. I have been in Russia several times, in Novosibirsk twice with CodeFest, and here in Moscow, and then also in St. Petersburg. But let's go on. So interoperability is something that you really should care you have to care a lot of attention. And it's a problem that is very common. Normally, we talk about interoperability between parts of our software, different layers. And the tools that we are going to see also address the problems between, let's say, two layers in the same application with .NET, of course. But I want to go deep dive in something that is a bit more advanced, so interoperability with native code and also using techniques that use unsafe code in order to improve a little bit the application without going too much unsafe, because we want to go in production without leaving our heart on the table, of course. And this is extremely important. One of the problems that we normally have, even if we have only .NET code, is reading, for example, a file format. And for the demos, I picked one of the most classic file formats, the WAV, the audio sound file format, which is very simple, as a header at the beginning, and then contains the data with the typical stuff of the audio. This is a classic problem because when you open the file, you really don't know what's inside, and you have to interrupt to understand how to deal with the structures. And one of the problems is that not always the structures are the same, the fixed size. So if there is something dynamic, well, in the past, .NET has not been the best language to deal with a type that is not well defined. Either you generate the code on the fly and you have the exact type for that structure, because anticipatively you cannot tell anything. Or otherwise, you have to adjust the things on the fly, and often this costs a lot of time in terms of memory copying and so on. So the goal of this topic is to understand how to get rid of these problems to improve the performance. Also, we will see at the very end the portion of the code that can improve the interoperability with a first-in, first-out queue, namely the pipelines. So this is the file format of the Wave file. It's pretty simple. I mean, I didn't pick like the JPEG of the H.264 video format because it's far more complex. It requires to lose a lot of time to explain the parts. You don't have to care about most of the concept here because most of the part here is fixed. Then you have a few things around the subchunk 2 that needs to be dynamic because there are the custom things. And finally, there is the data that can be in different file formats. You can have like one sample for 1 byte, or you can have multiple bytes per sample, depending the resolution, if it's 8 bits, 16 bits, and so on. If you want to interoperate with C++, what you are doing, what did you do until now? So what's the point of loading a thing from C++ for here? The C++ code is very simple. You have a structure, you declare the size, and then probably you want to also declare something on the .NET side, miming the structure and taking care of declaring the struct layout in a way that is sequential. One of the things that is very important is packing, because you will not know exactly how things are put in memory unless you have the packing that is fixed. You risk to have the allocation that does not match the exact file format on the file. By the way, if you are just interoperating with another system and you do not depend on a file format, one of the system is to decide a pack that is arbitrary. The important thing is that matches the two. So you can say, for example, packing 8, you align it on a 64-bits word, and you declare the same on the other side. Before looking at the pinvoke declaration, let's see at the code here. So the demo part in C++, this is a very, very simple part in C++. It's that you have a read file with a modern C++. We know that the vector is like an array, it's a contiguous memory. And you end up in loading the file and so on. We don't care about the various things. And when we read the content, we simply return the pointer to the buffer. This is because I already loaded in memory before when I open the file. And I decided, in order to show the benchmarks, to just return a pointer. The idea is to measure the round trip to C++ without measuring the IOs, because otherwise we are measuring my disk, which is not the best thing to do, okay? So I really want to make a round trip to C++ in order to measure the bad part, but I want to minimize the amount of time that can depend on the machine. And we have different ways of reading. So given the handle of the file, or what I believe is a handle here, I can return a pointer to just the wave header and reading it all. I can return a pointer and void star. And then this is probably the fastest way. Of course, I have to guarantee that the length is OK, but I cut away all these checks in order to make it faster, as fast as possible. The matching part on the native interop, by the way, this is the wave header that you have seen on the slide, and this is the way I declare the packing. When I switch to .NET, I simply declare this kind of declaration, right? This is very popular. There's nothing special here, unless these two parts. So when I want the .NET to make the interop for me, I can declare the WAV header here because I have a matching structure in .NET that exactly can be mapped to the buffer that I am going to load. So .NET will automate the core CLR will take advantage of this declaration in order to understand how to load the data for me. And this is a good way because you don't have to care about anything else. The problem is that if you have dynamic sides of the data, it won't work because there are very limited things that you can do when you declare the pinvoke stuff. And you are far more powerful when you can return just a pointer. And you can return a pointer like in this case, or you can return just an int ptr, and in out I can also return the length. And we will see them in a moment, the difference between those. Basically, the slides just repeat what I just said. I mean, the int ptr is good, but we will see that there is a difference. Now, there is a long-dated problem, let's say, in the language space in general, okay? If you remember the old times, C and C++ is a value-based language. That means that basically when you pass something as a parameter to a method, you copy the entire data structure. And you know that in C and C++, there is no difference between a struct and class. They are basically the same. There is just the visibility of public by default in structs, but they are exactly the same. And if you pass a class to a method, the entire class is copied and is called the copying constructor for this reason. In the very, very old times, that probably only me remember in this room, there was VB5. And VB5 was a value-based language. Then suddenly, Microsoft, after a few years, said, oh my gosh, it's too slow. And let's switch to a reference-based language. And so they changed entirely the language in order to pass references instead of values and not to have copies anymore. And they dramatically removed a huge amount of copies, and VB6 was super winner and had the successful life that you can read on the ancient book of the Romans. Okay, that's basically the idea. Now, after many, many years, we had .NET. And when the designers started talking about .NET and the languages in .NET, said, well, we can have both. Why not? We want to have the power of the value types because are copied, so I don't mess up with the caller that can see the changes in there. But I want also to have the power of the reference. So we have value types and reference type. Okay, we have both. The problem is that we have problems in both cases. So in the allocation is heap involved, so we have problems with allocating too many objects because the GC before or later must get rid of the allocation and take some clock cycles to throw away our memory. On the other side, when we pass a structure, we know that, oh, pay attention, because if you copy this stuff, you spend a lot of time in copying the memory on the stack, even if it's just a copy, okay? We don't have the GC, but we continue to have the copy. And so if the structure is very long, it's quite a mess. And so what happened? We now have what in C++ always existed. So basically, the references. The references are basically pointers, but are nice pointers. This means that you can access the memory pointed by the reference as it was a view. And you can watch at a certain part of the memory. Okay? It's exactly the same. If you have the power of write, you can change exactly the memory that is pointed to. If you have the read-only power only, which is very important. You can just watch, but you cannot read anything. And this is enforced by the compiler, which is extremely important. Because the compiler warns you, oh, sorry, you have a read-only reference, and so you cannot do anything nasty. You can write, you can only view, okay, for your eyes only. This is an example, very simple. We have point as a structure in the sample. I can declare a ref point, okay? I want a view on the point. And P is basically watching the point and is able to change the exact value that are inside the point, okay, because the structure is not copied anymore. If you remove the ref, the copy happens, okay? Then we have more powerful things. We have the ref struct. The ref struct is a new kind of type that is able to advise the compiler that you don't want to have any reference type inside the structure, for example. So this guy will only live on the stack and is guaranteed not to be taken in account with the GC. Because one of the mess point of the structures in .NET is that you can mix reference type with value types. So if you have a field that is a reference type, like a string inside a structure, you have mixed behavior. You copy, and when you copy the reference, and so on. Things are not exactly as you expected. Now you can enforce to have everything on the stack with the ref structs. And you have two guys, the span and then read-only span, of course, because it is extremely important. The result is that when you use these guys, you don't have any GC due to them. Of course, you can have GC for other things, but basically they don't provoke any allocation in the heap that will cost you something on the GC. It's basically meant to have a view on contiguous region of memory. This means that you can replace every array with a span, and it works very nicely, because every time you pass an array on a parameter on a method, you can replace this parameter instead of putting array of byte or array of string or array of something with a span of this T, with this type. And this is extremely powerful because you can do exciting things like slicing. You can take a part, slicing is like a substring, but we know that the substring allocates a new memory with new strings and so on. So it has a high cost, but the slice has not, and is GC free, okay? So on the left, you can see the basic, simple way that is when your memory is just a byte, is a single cell. But on the other part, it's a bit more complicated because in memory, if you want to visualize what really happens in the RAM, inside your PC, you have UTF-16 is the representation internal to the string, right? And so basically, you have also the endianness. This is why they are aligned on the right. So the H is here, the 4800, and so on. This means that basically, when you deal with the structures, you have to really understand what's happening here and what kind of T you have. Okay. So these new tools are really super interesting. Let's see our WAV example. That's extremely interesting. So the first point is to read the pointer from C++. So we read the content, okay? And then we obtain a pointer, either as an int PTR or a PTR. Outside the types that we will find a lot of articles on the internet on span of T and memory of T, when we deal with unsafe things like int PTR and pointers, raw pointers, you can build a new span that takes a pointer, one of the two, it doesn't matter, and specify the length, because of course you don't know exactly how can you go far. Of course, if you use this version, if you use this version, of course you have to specify in your project that you are dealing with unsafe code and use the unsafe keyword to specify it. Now you can build a span of byte. You exactly know what are the constraints of your memory, and you're basically done with the unsafe stuff. So from here on, you are managed. If the premises are wrong, you will have probably an exception or something bad will happen. But if the premises are right, you are done. And now you are safe to slice the memory, even if it's unsafe, and use it as it was a traditional array. And this is extremely important. You have two different possibilities. The first one is to obtain a span of bytes. So I want just the stream of the contiguous memory as an array of bytes. And the second is that, oh, well, I know that this pointer is a WAV header, and so I specify the structure. But of course, I have to know very well what is the exact memory representation, because they have to match, the bytes have to match exactly. So the previous declaration of the WAV header is extremely important, that is correct. Now, what can you do with that? The first thing that you can do is that you can transform the span of byte in a span of one WAV header. It's a kind of cast that is, of course, unsafe because it's dangerous. You are giving the guarantees, writing this line of code that you know that you can cast this span of byte in a span of WAV header. And this is basically the same when you cast something using one of the many casts, like a reinterpret cast in C++. It's up to you. And if you want, you can also materialize on the stack the instance of the WAV header. So, okay, I want a WAV header here. I want to materialize one because I needed to access it. Probably you want to change it some parameter and then save back to the disk, okay? And you can do this in two ways, like memory marshal read or unsafe read. The other possibility is to get, I don't want to materialize a new one. I just want a reference to the original stream of byte, but I want to see that as a reference of the WAV header. So I don't even copy the structure locally on the stack, okay? And I obtain a reference to it. And this is extremely powerful. Of course, this requires that you have good knowledge of how memory works. And I highly suggest you to make your tests using the memory window that is inside Visual Studio that can give you the exact representation of the memory there. Otherwise, you can be confused on what's happening with these statements. One of the cool things is that if you want to transform the PTR, so the pointer, in a reference, of course, the IL implementation, because this stuff was implemented in IL, is just to return the pointer, because they are the same, okay? So you have just a single IL instruction that will be probably optimized by the jitter, because normally with coming back from the call, you usually use the accumulator, and so the cost is substantially zero, okay? So let's see the performance result of all this stuff. I don't want to run the benchmark here, of course, because it takes more time and it's not worth the pain. But for your eyes, you have here the unsafe struct of the WAV header. This is fixed because you know that you can declare fixed things only in this way using safe code. And there is nothing special. I mean, it's extremely simple. The performance result we will see in a moment. So I run, I made two runs, one 1,000 and 1 million. You recognize these separators with the latest version of C#. You are not, are you already familiar with that? It's very good. I mean, I can confuse myself very often with the numbers, so that's good. I can repeat with these two performance reasons. So the first one is the pinvoke automatic. So I declared the read WAV header this way, and basically you return the WAV header. So you really have .NET taking care of everything, and you don't have to do anything else. This is a very small benchmark. It's a micro benchmark, which is probably too small to have a low error, but it works. The second possibility is to invoke manually. So I say, OK, I don't want to ask this automatic thing because maybe I cannot. So I read the pointer, and then I use this pointer with marshal PTR to structure. It's an old thing. You remember? Have you ever used it? OK. So you can take an int PTR and say, given this pointer, this managed pointer, I want this structure. And it exists since many years ago, since the beginning, I mean. The third thing is that you marshal manually everything. And this is terrible, I mean. It's a nightmare. Really, you are a memory guy. You remember everything. You play with the NDNS more than with your children. And, OK? And you know exactly how to pick and poke the things in the memory. Once you have done this, you take a coffee, and then you continue with the span byte on int PTR, which is the third way. So we can just read the int PTR just because we don't want unsafe here, but we need the unsafe because at the very end we have to transform the int PTR in pointer before obtaining a span of t. Okay. Then another one, I created this unsafe baseline, which is substantially just the call to C++ to have a reference number in the performance profile. We will see it in a moment. So now this will be repeated several times. The first one is repeated by creating a span of byte given the length. Okay, so just a row pointer. It's very similar to the previous, but now we have a row pointer. Then we have the span WAV header. So we say, OK, I want a span of WAV header. Remember that the span is like an array. So I just want one single element. This is the one. So it's an array of a single element. And then I repeat this one. I want a span of WAV header, but I want to play with the reference. So I want to obtain a reference so that I don't copy the stuff anymore. And again, I want a span byte, and then I cast this stuff to the WAV header. Another one is I start from the span of byte this time, and I materialize WAV header here. And finally, the last two are I read and materializing a read, and then finally I take the WAV header as a reference after reading this guy. This should be probably the fastest one, but as you can see from the performance results, sorry. The most important part is that the automatic one is not that bad because it takes 12 microseconds as a mean. But the Invoke manual, if you use PTR to structure, you end up in having also the GC working like hell. And so please don't use it anymore. If I use the single, and I have I want to play with memory and I remember all the endless stuff, I invoke every single field. The bad one, it takes much longer. But given that I cannot always use this guy, I have to use the other system. And as you can see, the last one that use int PTR, it's far slower than all the others. So you will not remember from the names here exactly what they do, but these are substantially the same numbers because the error plays a high number. So if you statistically, they are basically the same. And if you really care about this, the difference of these numbers, maybe you have other problems. So it's like an indicator. You should not mess too much with extreme performance research, okay? It should be your very, very last resort. The things that I want to stress here is please use the right tools, but don't exaggerate, okay? It will come time in where you really need to go further. Okay, we will open another chapter for that. But you are using the right tools if you use span of t and memory of t in this case. So definitely the way you have to interop with other systems and you want to optimize the memory access is better now, and you have to use these tools because are the best in town. The numbers are substantially the same when you go to 1 million. Of course, the microseconds are different, but they are proportional. Let's say there is no magic numbers that can give you a different performance profile. By the way, I also created, for my own curiosity, a collection. I have a past in collections, where it's substantially very similar to the list of T. But instead of using the list of T, the indexer I replaced with ref T, you see? This is the new indexer. And this is the underlying storage, which is an array. So just using ref, you obtain a different behavior, of course, because you receive a reference, and every time you change the guy who you receive it, you are modifying the collection inside, which is not what you expect. So Microsoft cannot change the behavior of the list of T, of course. But the performance profile are definitely interesting. So if you look at the indexer here, we are definitely far better with the implementation of ref. This gives you an idea that this ref stuff improve a lot the performance. And if you are curious about the number, we can discuss later on outside the room, of course. So, there are tips here. So basically, the ref structs are allowed only inside the ref structs. This limited a lot the way you can use the ref structs in your code. So you should be very careful. Every time you try to declare a local ref structs, for example, you end up in not being able to do if, for example, you are inside an asynchronous method or in types that you cannot declare a field that is not inside another ref struct. This limit the possibility of using it. But it's also a good thing, because in C++ you cannot, but you can also shoot on your shoes, of course. And in order to avoid to be too much unsafe, the limitations are there for a reason. And one of the workaround for the asynchronous stuff is, for example, this one. In this function, in this method that is asynchronous, since there is an await, I cannot write this one. I cannot take a local variable with memory.span, for example. I cannot declare a reference. But if you declare a local function that you know that are pretty new in the language, you can use this local function to override the problem. Okay, it's a nasty trick, but it works. And of course, here, the difference between these two, we have 2 points. And if you try to, from the moment that you assign the variable, you get a copy in this case, and you get a reference in this case. So the 2 points here are different, and here are equal. So I want to put this in the slide so that you can watch it and discuss with me later if you want. So to override this limitation, there is another type that is extremely helpful, that is memory of t. Memory of t is a normal structure, so it's declared as a read-only struct. You cannot change the content of the memory type itself. Of course, you can change the memory that is managed by memory of t. You have all the many goodies like the span property. You can obtain a span property for there. It can survive the stack unwind because it's not declared on the stack, and at least you can save it. Okay, it's declared on the stack, but you can save it. And one of the things is that you cannot convert the span of t in a memory of t anymore. So once you obtain the span, you cannot return back unless you copy the memory. And this is extremely important for you to take in account. So as much as you can, you may want to deal with memory of t type, and when you want to consume the memory, you pass to use the span instead. And here there are some examples just to show you how can you use it, but it's extremely straightforward, so I can skip it, and if you want, we can discuss later. So this is the very basic. So these are the tools. But one of the reasons why these tools are there is that because we want to have a better performance in ASP.NET Core, which seems unrelated, but it is. Because if you see the benchmark from Microsoft in ASP.NET Core, they are almost close to the top 10 frameworks in giving the best performance on a server application, but they want to go beyond. They want to win. Okay? And we also want to win. The first 10, by the way, are like 1%. They are far away. It's a very, very small amount that make a difference. So you end up in, we are fighting really a battle that is very, very tiny. The pipelines API were created for ASP.NET Core to have a interoperability between Kestrel and the networking system in general and ASP.NET Core itself. Every time you copy something, you waste time. Every time you unlock something on the heap, you waste time. And we want to avoid to have these copies, this heap usage. You want to avoid GC, and we want to avoid anything that can waste time. So previously, we had to manage this thing with the Stream API, which, by the way, it's also not so obvious to use for many scenarios because it's everything inside. You can read, you can write, but you cannot always read. You cannot always write because there is the can read and can write. You can consume it. And you may probably get the length, but it's not absolutely guaranteed to have the length available. And you have strange patterns that you can use to consume correctly the stream, otherwise you get exceptions, okay? And at the very end, the most important thing is that you copy a lot of memory. So what's the point of the pipelines? The point is that we want to have a better API in order to consume a stream of data. And this is the reason why they designed this API to have a stream of bytes. It's not of T. It's just bytes. So we can only deal with byte. Writing a pipe can be done in two ways. The first one is extremely interesting because you ask to the pipe to give you a memory of T representing the memory that is owned by the pipe itself. So you kind of book, you rent, you ask for a bunch of memory and say, please, can you give me some memory so that I can write inside this memory? And then you will send over the pipe the content. So I don't want to allocate any memory. I don't want to spend time in doing anything. So you get this memory, and pay attention, because this memory is the minimum size that you will obtain. But you will obtain more because it's rented, and so you will have a lot of memory more. You cannot use just the memory dot length to make some to argue something. Okay, so the mem dot length is not something that you should use unless you slice it. Then you use the get bytes. Everybody is familiar with get bytes to read the bytes that are the conversion in UTF-8 of the message, and you put directly into the memory span. This is kind of new because you are using the memory span as a kind of filter that you use to write inside the memory that pipes own. Okay? So you don't have to copy it anymore. It's quite strange. I mean, if you look at it, it's like passing a pointer, okay? Because the get encoding, the get bytes, is writing directly into the memory that you rented. Since the pipes cannot know what you did with that, you of course have to inform that you want to advance for a certain number of bytes. So how many bytes did you write? You have to inform it. You have, okay, I wrote just 10 bytes or 100 bytes. And once you have done this, you want to advise the readers that the write is complete, because maybe you are advancing several times, and you don't want to advise the readers just after one advance, but you want to inform when you are in control. And so you say, okay, I am done. You can go on. This flash is not the same of the stream flash. Okay? You're not emptying anything. You're just advising the reader. And at the very end, when you are completed of everything, and you don't want to use the writer anymore, okay, we complete. And we know that there will be no more bytes that will be written in the pipe. Okay? The second one is more traditional. So for some reason, I already have the memory that I know I want to write. So somewhere, some copy will happen. I take this memory of bytes using the get byte and transforming it, so taking this wrapper of memory of T with the extension method that is called as memory, which is part of the memory extensions class. And then I write async the content to the pipe. This is important because I want to write an external chunk of memory to the pipe. And then I am done. So I have not need to advance. I have no need to flash because internally it's done for me. And again, at the very end, when I am done, I can complete the write. On the other side of the pipe, since this is a first in, first out queue, there is a reader. And the reader can use an asynchronous technique or a synchronous technique. The asynchronous one is basically very good because you end up in having a while true, so an infinite loop, and you just wait the task signal you that something is available. And that is it's a very good method. So you end up in spending most of the time inside this await and waiting that something will happen. And you read async the content, and you receive then this result. This result contains a buffer and also two booleans, that is concealed or is empty. So if the writer completed, immediately I can exit, and then I will enter here and can leave the infinite loop. Or if the buffer is empty, I don't have anything more to do, and I can exit. The buffer, pay attention because it is the read-only sequence of byte. And also we have the synchronous technique. The synchronous technique is just I want to test on the fly if there is something that is available. So it's like polling the pipe, and I want to test, is there something for me? I want to check it. I take what is there, and then I run away. And so I am synchronous, of course, and again, the buffer contains a read-only sequence of byte. What are these read-only sequence of T? Is a linked list of memory segments, which are the chunks, okay, pieces of memory that are not contiguous. So you have the chunk itself is contiguous, but there are many of them that are not contiguous. And you may wonder why there is this system that is pretty much complicated when you want to do many things. The reason is that because of the network. The primary reason was for managing the interoperability with Kestrel. And if you know how the memory in the lower parts of the networking system works, you know that you cannot have everything you expect in a single chunk. And maybe you have several packets, you have not enough space in the buffer to return everything. So these linked list chunks avoid copying too much memory in the lower layer, and that's the best way to give you the performance that you need. So basically, this means that every time you want to read something, you have to cycle all the segment and consume what you have. There is no concrete class that implements this read-only sequence segment of T. It's not a problem. It's a very simple class. I watched inside the tests for the correct FX. You just derive the class, implement a few things, and you are done. So if you want your own implementation, it's straightforward. You don't have to fear it. One of the examples that came into my mind was, why can't I use this system to transform the stream of a process and read on another process the result? You know that in Linux, the pipes are the master way of interoperating between processes, right? So if you want to run a process and receive back the stream of bytes, you have to deal with the standard input and standard output. That's the way it works. And they are extremely important in NetCore, even on Windows, because you don't have anymore the app domains, the secondary app domains. And so if you want to run something and then unload the assemblies, you have to deal with it in a different process. So dealing with different processes is more important now than ever. This master process is simple. Basically, we open the standard output, and we copy the file stream to the standard output. It's finished. Nothing else. What is copying? This NASA picture. OK. I love rocket science. Everybody. Then, what happens on the slave side? So the part that should read. So I run the main, I get the full path of the file, blah, 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 and then I process the standard output of the other process. What happens? I open a pipe. I create this process executor that basically takes care for the demo purposes of running the master process. And I execute this stuff, and I simply copy this to the target, which is a pipe writer. So the target is a pipe writer that received the conversion of the stream. There is an extension method that transforms the stream to the writer. Okay. Once I have done that, I retransform this to the stream because I have to save the result into a local file. And so I open the stream for a file, and I take the pipe reader, and I copy to async to the target stream, which is a very simple loop, as you can imagine, that read async, as we have seen on the slides, check if it's empty or we are done, and finally iterate over the segments of the linked list that we were mentioning before. Every time I receive these memory chunks, they are read-only memory of byte, and I can save it straight to the stream of the new file that I'm writing. This is basically one simple example. If you want to see the demo running, we can discuss it later on the stand. Then because my mind is sick and I have a brain that is really tortured me on the night on strange demos, I started thinking to a strange use case. So what if we want to chain several pipes together and chaining the reader with the writer and the writer with the reader and so on, so that we can build a kind of transformation things that happen on the fly. So my point was, I can write a block that takes care of reading the wave file, isolate the data, makes then shoot the data outside, and another block makes the forward Fourier transform for the data, for the audio data, transforming the time and frequency, of course. And then I can work on the frequency, and then I can make some kind of filter on tweak the audio stream. And then I can make the fast Fourier transform reverse back in order to go back to the original time domain. And finally, I can write the new file. It looks like a strange use case, of course, but I know I'm sick. That's why I started thinking to this. So before this slide, let's see the demo for another example. In order to introduce you to these blocks, I want to show the pipeline console. So basically, what I was thinking is, what if I have a file source block and the file writer block? So basically, I started thinking to a block that can read something, and then the same content is written back. And I chain together with this connect API. We will see the source code in a moment. And then when I start, they are chained together, and I obtain the copy. First use case. The second is that what if I introduce a no operation block in the middle, so that I can test that effectively the data is copied correctly, and I chain with multiple blocks together. Okay, that works. And when I start, everything gets copied. What if I want to intercept the data and write in intermediate log, so that the file source is connected to a logger that then is written on the disk on the other side? So I have a kind of T in the middle. And then what if I want to take a file, put a pipe that is a one-to-many, and then to each one of these many, I want to connect other pipes, each one writing different things on the disk. So basically, I have multiple copies, okay? And I have the target 1 and the target 2. So file source is to the one-to-many, and then I have these two guys, and I connect these to the file writer 1 and 2. Then I totally lost my mind, and I have also the many-to-one. This basically is they are joining multiple writers to a single reader, so that I can finally write the content that is a merge, okay? And this use case basically means that I have a file that contains only ones, so 1, 1, 1, 1, 1 in binary, another file that contains just the twos, 2, 2, 2, 2, 2s, and the third one is a strange guy that basically, thanks to the many-to-one, do a very simple thing that is the sum. So we'll write 3. Okay. And that's it. I mean, so if we look at the file source, we have this stuff to connect. Have you seen? I only have to connect one to each other. I have to connect the writer to the reader and to put everything together. And we use exactly the same API we have seen on the slides. So there is nothing else. From one side I write, on the other side I can read. I don't have to care too much. The good thing is that you can advise the pipe how much data are you reading when you want to consume only a portion of the available part. And when you tell this stuff to the pipe, you end up in having being advised as soon as you have more data. So think about that, for example, I want to send the WAV data, but you know that there is not enough data to make the Fourier transformation because you require a minimum amount because the buffer cannot be a couple of bytes, okay? So you need more data to process the amount of data. And this happens when you want to you require additional. So if you want, you can say, I want to just consume this window because I have too much, and I want only consume, let's say, 2K. And the other thing is that I don't have enough data. Sorry, I don't want to read now. And you continue. Okay? And they will propose you, the pipe will give you the same data plus the additional one as soon as it is available. This is extremely interesting. So I can show you all the other stuff. For example, the transformation of the float to int into float is important for making the Fourier transform, because you know that you have to transform the domain. But this brings another problem, that you have to convert the stream of bytes into float. And you have the endianness problem, and you end up in having to deal with the marshal cast that we mentioned before in the presentation. So once you have done this, the very last point is that we finally have the wave file source, which it's very simple. The wave file writer that basically takes the same header of the original and write the data that is coming from the pipe, and a bunch of structures that deals with the additional headers that are inside the wave, which are not very relevant for the moment. Here I have the Fourier transform. And what happens that here I have this T3 transformation, F12, and I compacted everything to 3 blocks to make it simpler. And you have a wave file source, and then a vocoder and a wave file writer. So basically, it means that we can start from here, being the bug.NET Core application. I can delete this one. And they take this initial thing.
Передаем сигналы точного времени. Начало шестого сигнала соответствует 15 часам московского времени.
And when we are done this, we can run our demo. It just processed the data, as you can imagine. Okay. It takes some time to make all the computation. We have this target file.
Передаем сигналы точного времени.
Начало шестого сигнала соответствует 15 часам московского времени.
Look at your watch, 7 o'clock.